The aim of this presentation is to explain the trends in first ionisation energy as we go across period 3. So on this table, going from sodium to argon corresponds to going across period 3. And according to this list of first ionisation energies, there's a general increase going from here to here, but with one or two notable exceptions, like from magnesium to aluminium, where there's a drop, and also from phosphorus to sulfur, where there is a drop. On a graph, the first ionisation energy trends and patterns might look like this. Again, for an A-level graph, make sure all the plotted points cover at least half of the area of the paper. And you can see going general trend, so the general trend is that first ionisation energy increases across the period. Now, first ionisation energy is a measure of how difficult it is to remove an outer shell electron, or the outermost electron. So if we imagine that we call X gas any of these elements, the first ionisation energy could be represented by X gas produces X plus gas plus E minus. So it's the energy needed to remove 1 mole of electrons from 1 mole of gaseous atoms of the element to form 1 mole of gaseous ions, each with a +1 or unipositive charge. So that's what the measure is here. And so in essence, the first ionisation energy is measuring how strong the attraction is between the nucleus of the atom in question and that outer shell electron. So overall, the first ionisation energy increases across the period because across the period, so reasons, across the period there are more protons in the nucleus. So there are more protons in the nucleus. So the nucleus gets more positively charged. So nuclear charge increases. And the shielding, that's the impact of full shells of electrons between the electron being removed and that nucleus. So shielding stays constant. So that general trend can be explained like so. In order to start to address the differences, the exceptions to that general trend, so particularly the magnesium to aluminium drop and the phosphorus to sulfur drop, it's important to start to consider the finer electronic arrangement of the atom. So instead of dealing with shells, now dealing with subshells and indeed orbitals within those subshells. So the first thing it's important to be able to do is to appreciate what the full electron arrangement of each of these atoms is. So if we allow a shortcut, if you like, where we call Ne in a square bracket here, Ne then represents 1s2, 2s2, 2p6. We could represent sodium as Ne with a 3s1 electron. Magnesium, Ne with a 3s2. Aluminium, Ne with a 3s2, 3p1 and so forth. So we'll come back to that in a few moments. So let's focus in on this drop between magnesium and aluminium. Now you may have seen diagrams like this which represent the subshells and the orbitals within those subshells within atoms. So in these diagrams, one box there represents an orbital. And the orbital can have a maximum of 2 electrons in the orbital. So in the 1s orbital, so hydrogen for instance, hydrogen is 1s1, whereas helium is 1s2, so 1s1, 1s2. The next electron for lithium goes in the 2s1, then beryllium 2s2, and so on. The 2p fills one orbital half full at a time, then like so. Then we get to the sodium. So sodium is 1s2, 2s2, 2p6, 3s, oops, move that back, 3s1. Magnesium 3s2. And then the first of those elements which disobeys that general increase across period 3 is aluminium, which is 3p1, like that. So 3s2, 3p1. Now, to explain this away, we can use this CDSRE logic. Chemists do some rubbish experiments, but what this refers to in this example is the charge on the nucleus, distance of that outermost electron from the nucleus, any shielding that that electron experiences, any repulsion that experiences, and finally the energy of the sublevel. Okay, so in this example, what we're trying to explain is why it is that magnesium has a higher first ionization energy than aluminium, which is unusual. So let's start by checking out the charge. Well, aluminium has a higher charge on its nucleus than magnesium, so considering the charge just doesn't make any sense. Similarly, aluminium is a smaller atom than magnesium, so the distance actually decreases moving to aluminium, so that doesn't make sense either. Shielding, well, both magnesium and aluminium are in the third shell, third period. Their outermost electron is in a third shell orbital, and therefore the shielding, not relevant. Repulsion, well, if anything, the outer shell electron in aluminium is not spin paired, so would have less repulsion than that in magnesium, so that doesn't make sense either. So the explanation must refer to the energy of the sublevel. And in reality, the 3p sublevel here is just ever so slightly higher in energy than the 3s sublevel of magnesium, and therefore that outer shell electron in aluminium, the outermost electron in aluminium, is just a little bit easier to remove than predicted. Let's have a look then at explaining this. So the first thing to do to explain this clearly is make it really clear exactly which electron is being removed. So the electron in aluminium being removed is the 3p electron. So the 3p electron of aluminium is in a higher energy subshell than the 3s electron of Mg. So that explains why aluminium's first ionization energy is a little lower than magnesium's. So we've dealt with the general increase, we've dealt with that. Now let's have a look at this general decrease between phosphorus and sulfur. And to do that, let's revisit that diagram that we had earlier. So remember, these electrons will fill 1s2, 2s2, 2p6, 1, 2, 3, 4, 5, 6, 3s2, 3p1, 2, 3. So that will be the electron arrangement of phosphorus. So phosphorus is 1s2, 2s2, 2p6, 3s2, 3p3, versus this one, which is for sulfur, 1s2, 2s2, 2p6, 3s2, 3p4 this time. So again, let's do the charge, distance, shielding, repulsion, energy of the sublevel. Well, the charge on the sulfur nucleus is higher than the charge on the phosphorus nucleus, so that doesn't make any sense. The distance between the nucleus and the outer shell electron in sulfur is lower than the distance between the nucleus and outer shell electron in phosphorus, so distance doesn't make any sense either. Shielding, both of these are period 3 elements, so they have the same number of full electron shells between the nucleus and the electrons being removed, so that makes no sense either. Energy of the sublevel, well, the 3p, the 3 orbitals in the 3p are all degenerate, so in actual fact they have the same energy as each other, so it's not that one this time, so it must be repulsion. And it relates to that spin pairing of the electron in the 3p orbital in the sulfur atom. So, to explain this one here, again, start off with saying what those electron arrangements are in some form or fashion. So in sulfur, the outermost electron is in a paired 3p orbital, but in phosphorus the outermost electron is in an unpaired 3p orbital. Full stop. Well, so what? Well, that kind of starts that explanation off, but the so what becomes this. The outer electron of sulfur experiences some spin pair repulsion, and that helps to explain why that ionization energy is lower than the ionization energy, the first ionization energy, that being of phosphorus.